In this lecture, we will start with the differential calculus. The very first thing that we will discuss in this are the ordinary derivatives, and then we will discuss a special kind of derivative which we also call a directional derivative or a gradient, and we will solve some examples on this one. So let's first start that we are having a function f, which is a function of one variable x, and then this is called the domain of it, the variable of this function. So the question is that what a derivative tells us. So a derivative tells us the change in the function with respect to its domain, with respect to its variable. And if the derivative comes out to be more, the change will be more. And in other words, we call the derivative is a slope. So it gives us a slope of a function. Let's say we are having our coordinates. First, let's understand this one, that this is our x-axis and our function is along this axis, the y-axis. Now let's say we are having the function like this. So this is the function, and this is actually f of x along this axis and x along this, and this is the attitude of the function or the behavior of the function. Now if I write this one, for example, I consider this point. So this point on the x-axis is at this value. Let me call this value is x1. So its corresponding y-axis value is f of x1. And let's say this is another value here, and it is on the x-axis, it is x2 value, and this value which is corresponding to the y-axis, this value is f of x2 here. Now if I want to find the change in a function, then the change in a function delta f of x is the change in the function, while change in the variable is delta x. And this I can write is equal to delta fx will be delta f of x divided by delta of x is equal to the value, the higher value f of x2 minus the lower value f of x1 divided by the higher value x2 minus x1. So it will give me the change in this function, and this change is actually this line. This is the change in the function, and it is this line, because it gives, these are the two endpoints here. So this is the change in the function divided by the change in its variable, and then I can write that it will be actually giving this line. So this line we can decompose into components. It is having this much along the x-axis, this much change in along the y-axis, it is having this much change. So this change is delta of f of x, while this change is delta of x. And this line is this divided by this line. This is the final change in this function. Now if I look over here, this is a big change in this function, but my function is actually not changing like this. The function means it skips the function. Like the function is changing this way, while it is just the change between these 2 points. So the change seems to be a straight line. but the function is not a straight line. It means I will have to reduce the step size. In order to include my function, I will have to reduce the step size, and then I can write that this is delta f of x divided by delta of x, and let me limit this thing such that delta x goes to 0. This is a very small change. So what will happen? Delta x means x2 minus x1, x2 minus x1. So this point will come closer to this one. How close? That much close that the difference between it is going to 0, the minimum possible, and this is then equal to limit, and delta x goes to 0, f of, this is f of x2 minus f of x1 divided by x2 minus x1. And now if I look at this one, this is giving me the differential change in this function. Means a step-by-step change or a very small change in this function. So I will be following the actual function, and this I define is the differential. I can write this one is d of f, means the delta will change into d with this condition, df over dx is equal to limit, and delta x goes to 0, f of x2, the function value at any other higher value, and f of x1 divided by x2 minus x1, and this I call is the differential. The differential are the derivative of this function, and we define this is the slope of a function. This gives the slope of a function, because slope is the rise over the run. This is the run along the x-axis, and this is the rise along the y-axis, and as this is the rise over the run, so we call this slope of a function, and the slope of a function gives us the variation of a function. If we will have a function, now this one, and then a function, let's say this one, so the slope of this one is here, while the slope of it is very less of this function. So the slope gives us the change in a function. When I consider a straight line, a completely straight line means like x-axis or any parallel line to this one, then I see here that the rise, the run will be there, but the rise on a parallel line to the x-axis will be 0 at any 2 points, and I will say the slope of the x-axis is equal to 0. Like slope of the x-axis or any line parallel to this one will be equal to 0. Similarly, if I consider the y-axis, then there is a change in the rise, but there is 0 change in the run, so something divided by 0 will give us the slope is undefined. This slope will be undefined. It is so small, too huge, that we cannot define this thing, the value of this one. Derivative is actually very important. We call them is the special derivatives, because some derivatives we consider like the df over dx. Now this is a space variable, df over dx or dy or dz. So it is the space variable, and it is composed of x, y, and z. We call these the space coordinates, and it is a special derivative. Special derivative. And similarly, we have a time derivative, which is df over dt. And this we also call the rate of change of a function or the time derivative, because the function is changing with respect to time. So this is the time derivative, or sometimes we call this as a temporal derivative. Now here I can write this, that this is actually the change in our function, and df will be equal, df is equal to df over dx into that small element, like df over dx is equal to df over dx. So I can write this in this way as well, and it gives us the change of a function with respect to a space variable. In physics, we define things either in space or in time. So these are the two coordinates, means we will write time then here, and then we can define this one in time, in space or in time. And now we discuss a special type of this derivative, because this derivative is completely abstract, means it is only a magnitude, it's just a number. And we now discuss the directional derivative, which is section 1.2.2, and we call this is gradient. And gradient is represented by an operator which we call the del operator. So let's consider this one. As I said that the derivative that we discuss is a special derivative. So it depends on x, y, and z. These are the space coordinates. Now if, for example, we are having a function which is a function of not only x variable, but it is also a function of x, y, and z, and let's say that function is t. It's a scalar function, and it is a function of x, y, and z, means it depends on the three space variables, and we want to find out the change in this function with respect to x, y, and z. So we will use the partial derivatives here, and we will utilize this relation. So I will write that the change in this function dt will be equal, according to this definition, it will be dt means the change in this one with respect to x. If I writing this in one variable, then it will be dt over dx along this, the dx, the x incremental change. And similarly, the dt, this is the x component of this one, dx. Similarly, we will have y component, the z component. So this thing is then equal, this dt is equal to this differential. I will now write in the partial differential. So it is called partial or curly partial t by partial x, and this is in dx plus partial t by partial y, and this is in dy, and the z change will be partial t over partial z, and this is in dz along the z axis. So our change will be the partial change along the three axes in this function will be equal to this. And now I can write this one like this as well, that if I write curly or partial t by partial x, and this I write in x unit vector, and then this dx and x unit vector, as it is along x-axis, so let me write it like this: is it's a dot product, so only the inner components will multiply, and this is curly t by curly y and y unit vector plus curly t by curly z and the z unit vector, and then I put a dot product here and I write the dx and x unit vector plus dy and the y unit vector and plus dz and the z unit vector. So only the inner components will multiply, and I can write this one like this as well. The dt is then equal to, means it's a scalar function, so I can write, means I can take this t as common from here, so I can write this partial over partial x in x unit vector plus partial over partial y in the y unit vector and partial over partial z in the z unit vector, and here I write the function, scalar function t dot dx in x unit vector plus dy in the y unit vector and dz in the z unit vector. And this thing I define is operator del. So this is defined as operator del, a vector derivative, and means it's a special vector derivative. So I can write that dt is equal to the gradient of t dot this one dx, dy and dz, as this is equal to r, so it will be dr, or I can write it as dot dl. This is just the length element dl here, and then this thing I can further write is equal to the magnitude of the gradient t and the magnitude of the dl and cos of the angle between the two. So this will give us the gradient of this function. So the gradient t is actually pointing in the direction of maximum increase of a function t. Here, gradient of t, if I write it in one dimension, then it is dt over dx. It's the same thing, dt over dx. It is a special derivative, but gradient of t, when it is df over dx, so it will be in the x unit vector direction. It means it is a special derivative but in a certain direction, and this magnitude gradient t gives us not only the slope but the slope in a certain direction. So it gives us the slope, the rate of change along this maximal direction. So the difference between the ordinary derivative and the gradient is that one is scalar while the other is a vector quantity. It's a vector derivative, and I can give you an example on this one as well. Like for example, I'm having a heater in the corner of this room, and that heater is producing heat. So the heat will be going around this room in all directions. So any point I start and I move toward the heater, then its derivative means this way, that way, or all other ways I go. So it is called derivative. It is called the rate of change in space of that quantity or that function. But among all these directions, among all these variations, there will be one direction in which the variation will be the maximum, and that direction or that change is called the gradient. So it gives you the maximum change direction in which the function is changing. Another example, let's say we are going to the top of a mountain. So there are so many ways to the top to reach. Every way to the top of it is called a derivative. But there will be one direction which will be the steepest, in which the slope will be maximum, and it will be a unique direction. It will not be means duplicated, or it will not be having too many values. It will be a unique value, and that one maximum or the steepest way we will call is gradient. So gradient is nothing else but a directional derivative. I can solve an example on this one. Let's say this is example 1.3, and example 1.3 says that find the gradient of r. R is here a scalar function, x square plus y square plus z square square root, and this is the magnitude of a position vector. So find the gradient of this one. If I find the derivative of this one only, then it will be just the change along x, y, and z, and no direction will be involved. But if I find the gradient of this, then let's see that it will give us a vector result, and the gradient will always be of a scalar function, not of a vector, because for the vector we will take ordinary derivative, then it will be just like a gradient, because vector presumes the direction with it already. And here this will be equal to, according to the definition, gradient t. So it will be this curly r over curly x plus curly r over curly y and curly r over curly z, and write the unit vectors, because our gradient is here. Our gradient is equal to curly by curly x and x plus curly by curly y and y, and plus curly by curly z and z axis. So here write the unit vectors as well with them. And now this is symmetric in nature, means whatever we get for curly r over curly x, it will be for curly y over curly r over curly y. So it is symmetric. Let's first find this one, curly r over curly x. So it will be, the power of this is 1 over 2, so this is 1 over 2, and then this one is x square plus y square plus z square, and it will be 1 over 2 minus 1, and then the derivative of this one, which will give us 2 times x, while the same we will get for curly r over curly y, but this will be just 2y. Here this one, these two are cancelling, and I will get this is minus 1 over 2, so minus 1 over 2, it will come down, and the first we will get x divided by r, means it will be 1 over 2, so it is just r vector, r magnitude, and then it is in the x unit vector, plus The next will come is y, and this is over r but in y unit vector, and similarly z over r in z unit vector. So this is equal del r, this is equal to, if I write this is 1 over r, then 1 over r is taken as common, x and x unit vector plus y and y unit vector and z and the z unit vector. This is equal to r vector divided by the r magnitude here. And r vector over r magnitude is equal to the r unit vector, just the direction of it, and gradient of r means that it is r unit vector. So the gradient of a scalar function r is equal to the unit vector r, means the position vector, it is changing along its radial direction or it is changing along r. So if this is our coordinate system, and here we are having our function the position vector, let's say this is O, and this is our vector r, this is our vector r, so its magnitude is r. This way or this way I can write, while this, when the magnitude is unity, then it is the direction in which it is changing. This is our r unit vector, means in this it is changing. So the spatial variation of a scalar function means the gradient of this is equal to the r unit vector, just the direction of it. It says that the distance from the origin increases most rapidly in the radial direction, and that is the rate of increase in that direction is 1, because here the slope here is 1, it is changing, means the slope is 1 and this is the direction in which it is changing. Similarly, there are some other examples of which we can find the gradient, like problem 1.1, especially problem 1.12. I hope you will be able to solve this one. The problem 1.11 and 1.12, one must solve these two problems, and even if solve the 1.13 as well, then it is also good. But problem 1.12 is very interesting, in which we find so many parameters from the given equation, and this is the gradient. We call it a del operator, or we call, in other words, is the del operator. Like here I have written this thing is the del operator is equal to curly by curly x and x, and curly by curly y and y, and curly by curly z. And this one is, you remember that for any vector quantity A, we have written that there are three ways to multiply this vector. The very first one is to multiply it with a scalar number and then the vector A. So it can be multiplied with a scalar number A, number means 1, 2, 3, and it will only multiply with the magnitude of it, and there will be no effect on the direction of this. Another way is that if we are treating two vectors like A and B are two vectors that we are finding their interaction or their product, then there are two ways to do this thing, either to dot multiply them or to cross multiply them. There is no other way to multiply two vectors. Dot, if the result is a scalar quantity or it is a translational dynamics, then we will use the dot product. And if one vector is rotating along the other or sweeping along the other, means it is part of a rotational dynamics, then we will use a cross product. So what if we are having the a scalar function t, then of this scalar function we can take the gradient only, and this will be t and gradient of t. And when we are having vectors, like we are having any vector function, for example, let's say we are having vector function v, and we want to apply this del operator, so it's also vector quantity, then the only way is that we write del and v. So the only way is either to use dot or cross here between them. When it is a dot, means del dot is, I told you, when dot is there between two vectors, it is the translational dynamics, it is movement in a straight line. And when it is a cross between two vectors, then it is involving rotation or rotational dynamics, or the sweeping of one along the other. So what we will call this one, that the gradient and dot combinedly, these two are called is divergence, is divergence. And when this gradient operator is with the cross product, then combinedly we can call this is curl. The rotation means divergence, moving from one point to any other point in a straight line, while curl is the rotation of, because if I look here, then this involves spatial variation. But when dot is with it, then that variation, but in a straight, in a translational dynamics, and we call this is divergence. And when this gradient variation is combined with the rotation, then it will give us the curl of a vector, then how much a vector function or a vector field curls. So this is, with the help of this, we will proceed to some other, you can say the gradient we have already done. So we will now discuss in a while about the divergence of a vector and about a curl of a vector, and we will solve some examples on them as well. And then we will move to the fundamental theorem on the gradient, then a fundamental theorem on a divergence and curl of a vector.